Okay, so we just saw what happened with the green triangle being transformed to the purple, and we discovered this idea about vertically shrinking instead of stretching, because we had a third of the y, and we talked about the domain and range and how that was affected by this transformation. Now we're going to look at what happens if we take this x and y, the purple triangle, and we apply another transformation using this direction here, negative 2x, negative 2y. All right, so I need someone to tell me the R, the red double prime values. So I'm going to go to Desmos, and I'm going to press plus, add a table. And in my table of values, I need you guys to help me out from the last table to the new table and tell me what the new vertices would be of this transformed triangle. All right, how about Miranda in the back?
0, negative 6.
So 0 and then negative 6. Okay.
Negative 6, negative 4.
And then negative 6. Negative 4. Thank you. And then?
Negative 2, negative 2.
Negative 2, negative 2.
And 0, negative 6.
And then 0, negative 6. All right, I'm going to make this what color, class?
Red.
Okay. And we're going to connect the dots. Boom. We're going to tell Desmos that we want this line. So we're going to connect all those vertices. Okay.
Yes.
So now we went from this green to this purple, and we had a vertical shrinkage. I don't know if that's like mathematical terminology or not, but now we're looking at what happens when we go from this purple to this red. So what did you guys notice on Desmos, on your graphs? What did you notice from this purple to the red? I'll take any volunteers. What did you notice? Andrew. You get Andrew. What happened?
The size doubled.
The size doubled. Like the side lengths here? Yeah. And we didn't discover this yet, but there's another cool thing that we're going to look at, and that is what happens to area when you take a side length, for example, and double it or triple it, etc. These are a cool relationship. It would get bigger, you're right. But we're going to find precisely by how much it would increase. All right, or decrease. So, in this case, you're right. This looks larger. Why is that? Andrew, why is it larger?
Because we doubled it.
Yeah, so we doubled. But then we also did something else, because we have not just a double x, there's a negative in front of it. And look at the y here, we also not only doubled that, but there's a negative. So we multiplied by negative 2. So what else do you notice? I saw a hand up over here. What else do you notice? It's bigger. What else? Is there a transformation that appears to have happened? Patrick?
It's rotated 180 degrees.
It's rotated 180 degrees. How do you know that?
That's a 90, another 90, 180.
Oh, so I can test your theory by connecting these vertices, and if it goes through the point of rotation at the origin and makes a straight angle, I know that that's 180 degrees. And that appears to happen at each of the vertices going through the center of rotation. Anything else? What was the rule for a 180 degree rotation? What was the rule for x and y? Do you remember that? And I didn't make you memorize it, but does anyone remember what the rule was for 180? Rotation? Mia?
X, Y, negative X, negative.
Yeah. Look at this. How is that similar to this?
Oh.
What? Oh.
It's negative.
It's negative? Negative. So this composition of transformations is playing out right here beautifully. It is twice the size, just like Andrew discovered, and he noticed that and told us. And just like Patrick said, it's a 180 degrees rotation. Mia reminded us that the rule is negative x, negative y, so this makes
Far out.
sense. It is far out. It's pretty far out. Now,
Out of this world.
I know. What happens? Okay, so that's pretty cool. All right, so we can end the video here.